Okay, let's apply our Newton's second law problem-solving process to another example. This example might seem kind of boring, but it introduces a really important new concept of the normal force. So in this scenario, we just have a box sitting on the ground. It's not moving, it's not doing anything. Here's our sketch, and now I'm going to draw a free body diagram. My object of interest is the box, not the ground, just the box. And a good coordinate system would be x horizontal, y vertical. So I'll place my object of interest at the origin of that coordinate system. Now I want to think about the forces acting on this box. We can assume we're on planet Earth, so gravity is important. There's the gravity force of the Earth on the box. If that were the only force, this box would be falling. But it's not. It's just sitting there, not moving. That must mean that there is another force opposing this, canceling it out so that the box doesn't accelerate. That force is caused by the ground or the floor pushing upward on the box. And we call that normal force. The normal force of the ground, G for ground, pushing on the box. Now this word normal sounds kind of funny at first. It turns out that normal is a technical mathematical term that means perpendicular. Normal forces occur whenever two objects are in direct contact and they point in the perpendicular direction of the surface of contact. So this normal force points perpendicular to the ground. If you were to push against a wall, there's a normal force between your hand and the wall, or between the wall and your hand. The normal force points perpendicular to the wall. So that's what we mean by normal, perpendicular force. So gravity is trying to pull this box down. The ground is able to support the weight of the box and provide an upward normal force. So let's do the Newton's second law equations for this problem. We don't really need to do the x direction. There are zero forces in x and there's zero acceleration in x. So let's just do Newton's second law in the y direction. Sum of the forces in y equals ma(y). And we have two forces. We have this normal force of the ground on the box. It's pointing in the positive y direction. And we have the gravity force that's pointing in the negative y direction. And if you use a little common sense, you can probably convince yourself that this box is not accelerating. It's just sitting there. So the right-hand side of this equation is 0. If that box is not moving, it's not accelerating. That means that the normal force equals the weight and that weight we've learned can be written as mg, where g is 9.8 meters per second squared. Now I want to point out something that's a little subtle in this example that gives students confusion sometimes. The normal force is not the Newton's third law pair of the gravity force. It is the same magnitude and points in the opposite direction, but it's not the Newton's third law force pair. The pair of the gravity force would be the force of the box pulling on planet Earth. This normal force is between the ground or the floor or table or whatever surface this box is sitting on and the box. So the gravity force is between the box and the entirety of planet Earth. The normal force is between the surface and the box. They are not Newton's third law force pairs. In this example, by coincidence, they happen to have the same magnitude and point in opposite directions.